I'm going to start by giving a very brief overview of why the Aristarchus Plateau is such a fascinating area, especially from a volcanological point of view. Then I'm going to talk about the unique perspective that radar brings, and then largely concentrate on mini-RF radar and what our team is doing to try and further our understanding of this really fascinating area. And then as we're talking about exploration science, we're going to discuss what this means for landing sites in this region. Okay, so Aristarchus Plateau is situated in the middle of Procellera. It's surrounded by the youngest Mare basaltic flows we know about from crater counting. In addition to that, on the plateau itself, it also has other sort of Mare-like features in the form of these large-scale rills that cut through the plateau. Its most prominent features from a volcanological point of view is this gigantic pyroclastic deposit that mantles the entirety of the plateau. And this is obviously great from a science point of view of telling us stuff about the deep interior of the moon, but also, as we talked a lot about during this meeting, is resources as well. You can get metals, oxygen, and as you can see from this figure as well, non-polar water as well. So a great place to land in that sense. It also has one irregular Mare patch, which could be an example of the youngest volcanism that's been on the moon. And from the Viner data as well, I've also identified silicic volcanism, both intrusive and extrusive. So in summary, you have all the eruptive styles, compositions, and volcanism sort of span the history of volcanism on the moon. So, what's not to love from a volcanology point of view? We've been studying Aristarchus from the beginning of radar studies, which started back in the late 60s and 70s with Earth-based radar, both from the Haystack, Expand, and of course Arecibo. And it gave us some interesting insights into Aristarchus, both the rock distribution around the crater and the rills, but also told us information about the pyroclastics themselves. But it was really the sort of late 90s and the upgrades to the Arecibo allowed us to get this real nice detail on the plateau of the higher spatial resolution. So as you can see from this P-band or 70 centimeter image, you can really make out the pyroclastic deposit by the absence of backscatter. And this is because you're looking at these micrometer-like grains and glass beads on the surface that are very smooth relative to radar wavelengths. So yeah, absence of backscatter. This allowed people such as Campbell et al. To be able to map out the pyroclastic deposit and also look at properties of it, including identification of potential shallow Mare on the plateau itself below the pyroclastic blanket. And if we look in now at a higher frequency, shorter wavelength, you're looking at the 12.6 or S-band at higher spatial resolutions, you can also make out this region in the center here where you've got these potentially shallow Mare patches and also these radar bright faces as well, which are orientated perpendicular to the rim of Aristarchus and so assumed to be associated with Ejecta there. So the mini-RF radar that's talked about in detail during the first part of this section, but basically it's an orbital SAR radar that's on the Lunar Reconnaissance Orbiter. Unfortunately, back in 2010, its transmitter failed, but this didn't mean the end of the mission. We've now gone from monostatic to a bistatic experiment where we transmit from the Earth. Used to be Arecibo, unfortunately, that's also failed, but we're still in business due to Goldstone at Expand. Do a lot of cool things with that by looking at the various bistatic angles, but what I want to talk about today is just sort of these the beautiful images, the radar images that come from it. So from Aristarchus, we have got nice coverage in S-band, covers a large portion of the plateau, and then some also coverage in X-band, including some collects, most recent of which was just 10 days ago. So we continue to get more data. You can see this nice mosaic on the S-band. You can see some nice details in there, and then you can see the equivalent with the X-band. So I'm going to go through some of the sort of features. So first of all, let's look at the extent of the pyroclastics. As I said before, radar's really good at mapping this. And if we draw attention to the red arrows to the north of this plateau, this is a region where there's a little bit of sort of a confusion or maybe disagreements between the extents of the plateau. Do they extend pyroclastics? They extend beyond the plateau into the Mare and the Agricola Straits, or are they confined to it? And that tells us something about the stratigraphy and the age. And so what we see from both the S-band and the X-band data, that they actually cover some portions of this Mare. And so some of the pyroclastics must be younger. We don't have a good age date in literature, at least from this region, the Mare, but the most closest associated one is about 3 billion years. So that hopefully provides some sort of, bookends in which it's going to constrain the eruptive history of these, of the explosive history of these pyroclastics. Another thing we can do is looking at both S and X band. We can also identify this area that's assumed to be these shallow patches, this higher backscatter region where you've got these shallow Mare on the plateau itself, highlighted by the red arrows. And what's interesting is, yes, we can see an S band. We kind of knew that from before, from the Arecibo data alone. We're also seeing it expand. So that tells us some more about the size range of the particles that are within this section of the pyroclastic blanket, down to about 0.5 centimeter or so grains of material that's being brought up, presumably by impacts of this shallow mare, and within the upper like 0.5 meter. And so to sort of look at this in a bit more detail, we basically compared the biostatic responses both within this high backscatter regions, the regions of the north, and find that there is a difference both in the S and the X band data. And this is important because if you want to go to the well, it's important from volcanology point of view, because if you want to understand or map out the shallow mare, this allows you to do it. But also if you want to go here to harvest pyroclastics, this might be a region you want to avoid because it's going to be full of these 0.5 centimeter grains that are not pyroclastic in nature. And so, you know, you have to sift through that in order to get the water, whatever resources you want for that region. And finally, I want to talk about these apparent ejecta features as well. These sort of radar bright streaks that cut across both in X and S band data. Bruce Campbell and others, when they were working on this back in 2008, speculated this was either due to secondary processes which are churning up blocky material, or as primary Aristarchus material. And so what we did is we compared it with the LROC data. And so what you notice that areas where you have these bright radar streaks, you don't see corresponding secondary craters. Likewise, where you see these secondary craters in LROC data, you don't see the equivalent bright radar streaks. But one place you do see agreement is these like small high albedo crater, fresh crater here, that's also that's radar bright as well. And so when we look at the narrow angle images, you see this crater. Yes, it's covered in blocky material. That's why it's sensitive. The radar's picking it up, and also it's why it's looking bright. But also, if you look at these secondary chains, you see there's no boulders around them at all. And so what does that tell us? Well, that's suggesting then that we're not picking up. Thank you very much. We're not picking up. See, these radar bright features are not representative of these sort of secondary process. They're actually representative of primary material that's been brought from Aristarchus and deposited into the Ejecta into the pyroclastics. And so what does this mean from landing sites? Well, there's been a lot of studies done into this. You know, obviously it's a very important area, and some of the more recent suggestions have argued for sort of a multiple phase approach to studying this region, where you go to multiple locations based on the various importance of those, you know, such as the Aristarchus craters itself, which is meant to have impact into subsurface of granitic Pluton, maybe. Look at some of the extrusive silicic materials and look at the blanket itself. So one of the areas we sort of want to call to your attention here is this red circle here. Now this region, one, you could sample pyroclastic material, of course. Secondly, it was identified based on this Christensen feature that is also silicic as well. This what they call is these knobby terrain, and so there could be so it's important from that to sort of, if you wanted to land there, to sample those. But also this has one of these radar bright streaks, and so this is actually in the area where primary Aristarchus material has been brought to that area. So in this small region, you could sample, you know, 3 different really important regions of the plateau coming to you, essentially. And so that's where we'd suggest land. Now, of course, in the other way, if you want to interest in the resources themselves, then you should avoid anything that's radar bright at all, because as I said before, that is areas where the pyroclastic blanket is contaminated, and it's going to be harder for you to mine that. So I'd suggest going somewhere up to the north here, where the blanket is much thicker and less contaminated. And with that, I'll end, and thanks very much.